So let's talk about data. When we start talking about, again, these terms of parametric versus non-parametric statistic, quantitative versus qualitative, we need to define every one of our variables based on the descriptive units of that variable. So there's, broadly speaking, four types of quantitative data. And again, quantitative means we've assigned numbers. There's nominal. Attributes are the only thing named. It's the weakest. So nominal data is all those numbers are is basically just units for us to be able to do mathematical analysis with. They don't represent anything more than names. So 1 represents a group, 2 represents a group, 3 represents a group. But those groups are not necessarily more or less, better or worse. They're simply names. They're nominal. And then we have ordinal. The attributes can now be ordered, but the ordering information does tell us that 2 is more than 1, 3 is more than 2, but the only thing they tell us is the order that they're in. The difference between 1 and 2 may be very small. The difference between 2 and 3 may be very large. So again, nominal data might be, for example, 1 is men, 2 is women. We want to create a variable. We want numbers because we want to do just a statistical analysis, but those numbers don't have meaning. They're just labels. Ordinal might be, for example, the order that people finished a race. So there's first, they had the very best time. There's second, they had the second best time. There's third, they had the third best time. But the first might be they ran the race in 5 minutes. Second might be they ran the race in 4 minutes and 59 seconds, 1 second difference. Third may have ran the race in 5.5 minutes, 30 seconds later than the others. So again, all we have is ordinal data. Now, if we have nominal or ordinal data, this is often referred to as categorical or discrete data. In other words, it's non-parametric data. It's not data that we can necessarily create distributions out of and trust those distributions, nor can we come up with mathematical averages that are truly meaningful from that data. Now, as we move to the next level, interval, the distance is now meaningful. And normally, we're going to see interval data. Each interval between the numbers is approximately the same. So with interval data, we now have numbers. They're representing something, so they're like nominal, but they also have order. More means more of something, less means less of something. But also they have now intervals, equal intervals. So the difference between 1 and 2 is theoretically the same as the difference between 2 and 3, 3 and 4, 4 and 5. A lot of personality variables and a lot of opinion variables that are on a Likert-like scale, or a Likert scale, a 1 to 5 strongly disagree to strongly agree scale, is considered interval data. Now we can go one step beyond interval, and that is we introduce basically count data or ratio data. That the scale actually itself has meaning. So again, on a 1 to 5 scale, 5 usually means more agreement, 1 means less agreement. And the difference between strongly disagree and disagree and neutral and agree and strongly agree are effectively the same. I could do that exact same measurement with different numbers. I could have an interval scale that actually is -2 to +2. Strongly disagree is -2, disagree is -1, neutral is 0, agree is 1, and strongly agree is 2. I've changed nothing. I just use different numbers. So even though we have interval, ordinal, and nominal information in an interval scale, the numbers are still arbitrary. Ratio data, the numbers have an absolute 0. In other words, 0 means something. 0 means none of whatever we're measuring. Normally, we're going to see ratio data in objectively measured behavioral data. How many times someone does something. If you do something 0 times, 0 is meaningful. You never did it. If you did it once, but only once, 1 is meaningful. If you did it 4 times, the 4 is meaningful. It's not only labeling your behavior, it's not only giving order to the data, it's not only showing equal interval, it also is a meaningful measurement of the unit you're interested in. In other words, it's tied to reality. It's not an arbitrary value. And broadly speaking, this breaks us into 2 main categories. Parametric statistics, those with an outcome that are either interval or ratio data, and non-parametric statistics. The outcome is either ordinal or nominal. So if we have interval or ratio data, we generally refer to that as continuous data. And it's data that we can use parametric statistics for. And most of our descriptive statistics are intended for parametric statistics. So we're talking about distribution moments, and the moments are 4 moments. The moments are ways to measure a distribution. We can measure its center point, we can measure its variance, we can measure whether it's skewed, and we can measure its shape. So distributions do come in various shapes. Normally, though, most of what we're interested in psychology, behaviors, attitudes, psychological constructs, are on normal distributions. Very few people have extremely low scores, very few people have extremely high scores, and most people have kind of midpoint scores. But there are other distributions, and we'll talk about those as this class progresses. But for the moment, we're going to focus on that normal distribution, often referred to as a Gaussian distribution. So the moments or the parameters are characteristics that define that distribution. And ideally, we want a non-skewed, non-kurtotic variable with a mean and a variance measurement. So the mean is simply the mathematical point, and there are other ways to capture the center of a distribution, and we have to use those if we have a non-normal distribution. A normal distribution basically is symmetrical and bell-shaped. And that means that you have the mathematical mean, the mode, the most common response, and the median. If you put all of the responses in order from lowest to highest, what would be the midpoint of those scores will all be the same. When we find skewed, either positive or negative, now those 3 values stop having the same value. Generally speaking, in a skewed distribution, mode, the most common response, is going to be the top of the distribution. Median, the order that actually, if you just put every score in order from the highest to lowest, is still going to be dragged a little bit towards that skew, but not much. And the mean, the mathematical average, is definitely going to be pulled away from that. So again, if I actually have a skewed distribution and I report the mean, that's not an appropriate statistic to report anymore, because the mean infers that half of the people scored above and below. And if you look at the example at the top left, you see that actually if you use the mean as the center point of distribution, about 2/3 of the people scored below the mean and only 1/3 scored higher. So if I gave a mean and you assume that mean is the midpoint, it's not anymore. And that's why we need to make sure distributions are not skewed. Positive skew simply means there's extreme values to the positive of the scale. Negative skew means there's extreme scores to the negative of the skew. We also are a little worried about kurtosis, so the shape of the bell. So in the case of a non-skewed but kurtotic distribution, it's symmetrical, but it's moving away from that bell shape to either a tight point, for example, a leptokurtic distribution, where almost all the scores are clustered around the mean, or a platykurtic distribution, where the scores are spread throughout the distribution. There's not really a high midpoint. So the problem with a leptokurtic distribution is the mean is not just the center point at that point. The mean also is very close to what almost everyone scored. And again, if we're thinking of the mean as a point in the middle of a distribution, that's not quite appropriate anymore. And likewise, for a platykurtic distribution, again, the mean, it is still 50-50, but a lot of scores aren't anywhere near the mean. So we want normal distributions where the mean represents the mathematical average, the center point of the distribution, along a mesokurtic or normal distributed bell curve. So again, how do we actually calculate the distribution moments? Measuring sample is simple. So the equation here, and a lot of times when we see these equations and statistics, I'm often going to remove a lot of the notation and get down to just actually what's going on. So basically, what the initial equation here is y with the line over it is basically the mean of y. It's the mean of a variable. And what we're calculating is we're summing every individual score in y. Notice that the y has a little I, and underneath it, it says I equals 1. So that basically is telling us that y there represents a single score. We have the Greek symbol, Latin symbol for sum, and we have n above it. That means that we're going to need to sum all of the scores. So what that notation tells us is that if I have 30 scores, 30 people that gave me a score on y, I add up all 30 scores. And then I simply divide by the number of people that provided scores. So Sample variance in this case, that's our mean. Now, variance is a measure of how much distribution is on either side of the mean. So again, in this case, we have to calculate the mean before we can calculate sample variance. And what we're doing again is we have sum, and this time we're summing up the results of taking each individual score minus the mean squared and then added together. So again, if I had 30 scores, I would take each individual score, subtract the mean, and square it. Do that 30 times, add them all up, and then divide by n minus 1. This is going to actually give me my variance. So variance gives us an idea of how widely the scores differed from the mean. So parametric statistics make some assumptions about the shape of parameters or the population distribution. It focuses on the last three moments. It's focusing on the variance, it's focusing on the skewness, and it's focusing on the kurtosis. Types of parametric statistics include t-tests, Pearson correlations, regressions, ANOVAs. In fact, most of the statistical techniques we're going to use. And each test has its own set of assumptions. And as we talk about each test, one of the things we're always going to talk about is what are the assumptions this test makes. Almost all parametric tests make the assumption that your outcome variable is continuous, is not skewed, and is mesokurtic. It is not leptokurtic. It is not mesokurtic. Or not mesokurtic. It's not platykurtic. In other words, it's normally distributed. It's a bell curve. These assumptions must be met for valid results. And you have to test these assumptions yourself. The statistics don't test for assumptions. They assume you've already done this. So one of the first steps we're going to do anytime we run any analysis is to test the assumptions on our data. So just some quick little bit of history here. T-test was actually created by Gossett. Pearson's correlation was actually created by Pearson. He also worked on regressions. And Fisher is the person that created ANOVAs. And when we talk about each of these techniques, I'll get a little bit into the history of these guys because it is kind of interesting to find out who designed these statistics, why they designed them, and also, honestly, the feuds that these people had. So it's kind of interesting. Pearson and Fisher disliked each other fairly intensely and actually even attacked each other in various academic papers, while Gossett, the creator of the t-test, was kind of friends with both of them. So I just find those little bits of back history to be interesting, and I'm going to throw those in here occasionally as we run across them. Okay, so we're going to talk about experimental design. We're going to talk about the history of the research, cause and effective causal design, purpose and kinds of experiments, and causal generalization, and some practical skills. This really is just going to be an overset. We just kind of got through a basic refresher of the types of data and how we use descriptive statistics. We're now going to talk a little bit about the big picture of methodology. So just a brief bit of history. Experiments have been central to human existence from ancient times to present. However, most of our concepts of modern scientific examination of experiments is relatively new if you look at the totality of human history. So honestly, Francis Bacon was one of the first people to actually say that science wasn't just about observation, but it was about twisting the lion's tail. In other words, he's the first person that really kind of codified the idea that you don't want to just observe in science. You want to create testable hypotheses. You want to have a hypothesis that a lion will remain in rest unless annoyed, at which point it will attack. Now that's a pretty solid, easily you can go, well, duh, of course that's going to happen. But that's science's job. A lot of times when you hear a study that kind of sounds like common sense, just remember that sometimes when we test common sense, we find out it's wrong. So it is worthwhile testing common sense. So scientific methodology is based on the idea that whatever we're researching needs to be observable. So we have to be able to observe the variables we're interested in, and we have to be able to quantify and measure them. We need to objectively measure the variables that we can observe. We need to create hypotheses that by their nature have a null hypothesis alternative, that they can be disproven. And once we create a study, it needs to be repeatable. In other words, if we create a study in such a way that no one else could ever repeat the study, it might be still interesting, but it's no longer science. Science lives on the idea that we're looking at things that can be observed, things that we can agree on how they're measured, We're testing hypotheses that could be proven wrong in a way that other scientists could test our results if they wanted to. So as we develop that scientific methodology, we start to get the actual tools that come around with Mills canons, including the idea of a control group. In other words, if you're going to twist the lion's tail, you also need to know what happens when you don't twist the lion's tail. We look at the concept of random assignment, so that if we have different groups, the only way to make sure that there aren't pre-existing differences between those groups is to make sure that everyone has an equal chance of ending up in the control group or the treatment group. And finally, that we need to control all other variables to account for potential biases or confounds, again, if we're looking at causation. So let's talk about cause, effect, and causal relationships. So again, a cause, that which produces a result or an effect. The effect is the difference between what happened and the counterfactual, what would have happened if you had not done an intervention. So the counterfactual is basically the control group. What would have happened if people who received a treatment versus those that didn't receive the treatment? And again, we have the causal relationship defined by Mills canons. The cause has to precede the effect, the cause has to covariate with the effect, and confounds have to be ruled out. So experiments by their nature are striving towards causation if possible, but often don't quite get there. We can have descriptive studies that aren't even looking for necessarily patterns, they're just describing a behavior. We can have correlational studies where we simply look for the patterns, but we're not necessarily even trying to infer them to other populations. And we can have inferential, manipulatable causes where we're making an inference that what we find in our sample is something that we could also find and then use in an applied setting. So broadly speaking, within that kind of framework, there's all types of experiments. There's the true experiment, usually using randomization into groups, usually tightly controlled, and usually trying to make sure that we've hit all of Mills canons. But there's also quasi-experimental, where we can't use that random assignment or we can't have that control. And honestly, in organizational settings, whether you are working with individual clients, whether you're working with a school, or whether you're working with an organization, a lot of times all we have are quasi-experimental studies. We can look for effects, we can look for patterns, we can set up the study to at least make an argument for inference, but we can't really get to causation. We can also look at natural phenomenon, just looking for an effect in pre-existing variables. We can look for observational studies where we're observing, and those can be both natural, where we just observe behavior, or where we twisted the lion's tail, but in a way that people don't recognize. So for instance, if you're wanting to look at how people socialize at a restaurant, you could simply start taking notes. They have no idea they're being observed, and you start noting a descriptive study of how they behave at restaurants. If you want to know about how they behave at restaurants when they get their orders served to them wrong, you could actually contrive that. You could pay the waitress to always get the order wrong to create the situation you're wanting to observe. Now again, they don't realize they're in a study, but you have twisted the lion's tail. We can also do experiments where we're not involved at all. We're not necessarily observing, we're not doing direct study, we're not doing direct measurement. We're basically doing either content analysis, which is we're examining pre-existing data, we're looking at archival data, and we can also leave inferential statistics behind. There is no wrong or right way to learn about the world. And a fair amount of psychological studies have started with qualitative interviews, focus groups, and ethnographies. In fact, cognitive dissonance theory, so that's the idea that if your behaviors and your attitudes differ, it's easier to change our attitudes than our behaviors. Where the study of cognitive dissonance with Festinger started was actually a qualitative study. He joined a doomsday cult and did an ethnography of them. He studied them, he observed them, he took notes. Because what he was interested in is what happens in a group when they're a doomsday cult and doomsday comes and they're still there the next day. And what he found was that generally they didn't leave the cult. In fact, they doubled down. They got even more focused on believing in the cult, which didn't make a lot of sense, except again, how do you justify your behavior of having joined a cult for months, find out you're wrong? Well, you joined the cult, you can't change that. The cult was wrong, you can't change that. But you can change your attitude to make it feel like you still made the right choice. Based on that ethnography, that qualitative data, he then brought the same idea into a contrived experimental study with randomization, where he actually did his classic study on cognitive dissonance. So there's also different types of design methodology. So designs can be categorized according to whether the IVs are manipulated and whether random assignment is used into groups. So again, if you have true manipulation, you're in control of your IV, and you're randomly assigning people into being assigned to that controlled IV, you're in an experimental setting. If you lose one or the other of these, if you no longer are manipulating the IV or you no longer have random assignment, you're probably in some form of quasi-experimental design. And if you have no assignment and no manipulation, you're probably in a non-experimental design. And again, statistics don't really care whether you're an experimental, quasi-experimental, or non-experimental design. They're just looking for patterns. This is information that you need to know methodologically. Designs can also be categorized by the number of independent variables or predictors you have. A one-way design has a single IV. A factorial design has multiple IVs, which may also interact with each other. And finally, designs can be categorized by the level of the IVs participants are exposed to. Most classic experiments using random assignment are what we call a between participant design. So if it's a one-way design with a single IV, and each person can be either in group 1 or group 2, but not both, that's a between participant design. But we could also do it within participant design, where people actually are first in group 1 and then later in group 2. Same people exposed to both levels of the IV, that's within. Now, if you have multiple IVs, a factorial design, you could also have a mixed design where some of those IVs are between and some of those are within. Every design has its strength and weakness, and we're going to kind of touch on those as we continue through this class. So let's just kind of break down what all we're going to cover in this class. And one of the ways to look at it then is kind of what we just talked about. The question is, how many variables do you have? And are they within or between variables? And again, we're focused here on the IVs, because currently what we're talking about for this class is what's called univariate statistics. And the uni means one statistic, univariate, one variable statistic. That doesn't mean we only have a single variable, it means we only have a single outcome variable. So every one of these statistics has a single continuous DV. So the how many variable questions is based on how many additional variables are in your model. If the answer is only one, you just have a DV, you don't have an IV. That doesn't mean that you can't do some tests, but the tests that you're going to run are basically comparing your DV to known samples. And that's probably the simplest statistical test that there is, and that's either a t-test or z-test for independent samples. Now, if the answer is you have more than two, so that means that you are in a factorial design. You have two or more IVs. So you have a DV and two or more IVs. The next question is, are those IVs continuous or categorical? If they're categorical, we're looking at factorial ANOVA. If they're continuous, we're looking at multiple regression. Now, if you only have two IVs, so this means we're in a one-way design. We have an IV and a DV. The next question is that IV categorical? If it isn't, if it's continuous, so we have a continuous IV and DV, we're at correlation or regression. But assuming it's categorical, the next question is how many levels? How many categories? If it's only two, that takes us to a final question. Is it between or within subjects? Are people being exposed to both levels of the IV, or are they only exposed to one level? If there's only one level, that's a between design, and we do a t-test for independent measures. If they're exposed to both levels, that's a within design, we do a t-test for dependent measures. Now, if the answer is that we have more than two categorical variables in that single IV, again, we have the between or within subjects question. If it's between, we're at the independent measures ANOVA, and if we're at the within, we have the repeated measures ANOVA. So this is covering most of the statistics we're going to cover for the first half of this class, all in a decision tree, all based on simply two questions. How many IVs, what kind of IVs, and how are people being exposed to those IVs? Now, generally speaking, we want to use what's often referred to as Occam's razor. The simplest answer is always the best. So if you could run multiple statistics, always go with the simpler answer. So for instance, if you had a categorical IV with only 2 levels, you could still run an independent measures ANOVA. But the independent measures ANOVA has been specifically designed for 3 or more levels of that IV. Go with the t-test. Always go with the simpler statistic if you can. So once we've actually completed our statistical analysis, we found out if our p-value is met, if we've met the requirements, we can claim statistical significance. We also then want to ask, can we actually infer it back to the population? And generally, this is a process of logic, not statistics. So experiments are local. They consist of units, treatments, outcomes, settings, and times of your study. The question is, can you infer or generalize those variations in people, settings, treatments, outcomes, and times? We often refer to this as UTOS, both small UTOS and large UTOS. So small UTOS is your study. It's the specific operations. It's the specific people that were in your sample. It was the specific treatment study. It was the specific way you observed the DV. It was the specific setting of the study, and it was a specific time. How well did you design your study to make it easy to logically argue that your operations represented the bigger constructs, that your study guide represented studying, that your test represented performance, that your sample units equal the unit constructs? In other words, how well did your sample represent the population? As far as your actual treatment, the operations, did they represent other operations well? As far as your outcome, did it represent other outcomes? And your setting, is there something about your setting that makes it hard to generalize it to other settings? Did you do your study in a very rural, low education area, making it hard to generalize to a higher education, urban setting? And finally, no matter what, recognize that all of our studies are looking at human behavior, and human behavior norms and even kind of quantifiably measured objective measures of human behavior tend to change over time. So almost any study, no matter how well done, will over time become less relevant. It's one of the reasons we continuously do additional studies. So your practical skills that you're wanting to build in this program and specifically in this class is you want to identify claims about causes and effects in research. Are their conclusions reasonable? Did they make a reasonable argument that they have successfully checked all the boxes on Mills' canons? Check to make sure the conditions for causal relationships are met. Whether you're reading a research article or a media article, does the design warrant a causal conclusion? You want to create valid sources of counter and factual inferences in your own studies. So when you're reading a study, was the comparison group a reasonable facsimile of what would have happened without the treatment? And likewise, when you do your own study, are you setting up a study which has a reasonable counterfactual? And learn how to think about causal explanations and how to build them into your experiments. Add design features to get you closer to being able to make those inferences, even if you don't have cause. And we'll talk about ways to do that as well. And finally, kind of get a general understanding of how scientists make generalizations, how they take a study that often is very artificial and confined in order to make the requirements for causation, and then try to use logic and past theory to argue that it does generalize to a greater population. So just some quick canons of Cite 52521. Anytime you're talking about statistics, you want to do the following. Whenever you're writing out an analysis, you want to start with, what did you do? In other words, if you ran an ANOVA, the first sentence of any write-up should be, an ANOVA was run. If you ran a t-test for independent samples, an independent samples t-test was run. Always clearly identify to your reader what statistic you used. Because remember, every statistic has appropriate and inappropriate uses and various assumptions that have to be met. If I don't know what statistic you ran, and if you don't know what someone's statistic ran, you can't answer those questions. The next thing that should always be written up is, what were your variables? So specifically, what were your IVs? How were they measured? What were your DVs? How were they measured? In other words, you could say, for instance, a t-test was run comparing the differences between study guides and no study guides. The independent variable was the presence of a 5-page study guide. The other condition, the counterfactual, was no study guide. At which point, after being presented study guides, 3 days later, participants took a 50-item multiple choice test. That's your DV. Now you need to actually report the test statistics, and you need to basically tell, was the test significant, regardless of what the statistical information is. In other words, you always need to report P. Generally speaking, I suggest getting in the practice of always reporting to 2 decimal points anytime you're reporting any statistical information or even descriptive information, unless the P is lower than 0.001, at which point we're going to report less than 0.001. So anytime you're reporting numbers, including p-value, report it to 2 decimal places. The only time you'd break that is if you have a statistical significance of lower than 0.001, report less than 0.001. We never report a p of 0 because there is no such thing. P is a probability of being wrong. There's always a chance we're wrong. If it was significant, we're going to continue. By the way, if it wasn't, if our p-value was 0.07, 0.08, we're done. You reported the test, you defined the variables, you reported the test statistics, and you reported an insignificant p. You're done. If you reported a significant p, we've got to continue 2 more steps. If it was significant, we now need to report the effect size. So how meaningful was the difference? And also, if significant, what was the nature of the effect? So if it was a regression or a correlation, what was the direction? Was it a positive or negative correlation? If we were looking at the difference between study guide or not study guide, what were the means of those and standard deviations of the people that had the study guide versus those that didn't? I really want you to I would actually suggest printing this slide out and keeping it with you whenever you do your homework, because a lot of your homeworks are going to be reporting statistics and writing out the results. Make sure you do every one of these anytime you're reporting a statistical result in a homework or a test question. Anyway, like I said, thank you for listening to these 3 lectures for the first week. I'll continue posting these hopefully no later than the Tuesday of each month that the lectures are actually assigned. If you have any questions, once again, remember, you can reach out to the TA, you can reach out to me via email, we can set up a Zoom meeting, but also use that discussion section that's on Blackboard for each lecture. If you have questions, definitely post them there, and I hope you have a good week.